today we will continue to look at another example of a monad, so we get a little bit more of a feeling for what a monad is. So let's quickly remind ourselves. So last time we said that a monad in category theory doesn't just work for types as in Haskell, it works for any category C, and it's a functor from C to C. It's called an endofunctor. That comes with two extra pieces of data. So we have a return natural transformation, which goes from x to m of x for every x. And there's a join natural transformation, which goes from m of x to m of x for every x. Right. So return is saying we can take 0 layers of m and make 1 layer. Join is saying we can take 2 layers of m and make 1 layer. So all in all, we can take any number of layers of m and turn it into 1 layer of m. Right. And then we had some laws for these things, saying that if we first return in m of x and then join it back together, that's doing nothing. And if we return on the inside of an m, so that's an f map of m, and then we join it back together, that's also doing nothing. So return is kind of making spurious m-y things, but we don't get anything by making a spurious thing and then joining it back together again. And join said that there's two ways to join together 3 m's. You could either first do it on the outside and then on the inside, or you can first do it on the inside and then the outside, and that's the same thing either way. Right. I think it's helpful to look at the diagrams we drew last time to see what's actually going on. But most of the time, just like when you do a natural transformation, you do a transformation and you prove whatever Agda tells you to prove. Most of the time when you're trying to define a monad, you define a functor, you define the return and the join, and then you prove the laws that Agda tells you to prove. Right. So again, the laws are mostly here when someone else gives you some monad, then you know something about it because you have the laws. And we'll see next week why that can be important, or maybe at the end today. Okay, and then we also said that if you have these things, then you get the bind that we know from Haskell, except that we rearranged the arguments a little bit. So it says that we can lift a morphism from A to M of B into a morphism from M of A to M of B. And we saw that if we take this expression language as our notion of a monad, we proved that it was a monad, where we send the set to the set of expressions with variables from the input set. Then we saw that the bind corresponds to substitution in this language. Right. So if you tell me an expression for every variable, then I can carry that through the whole expression and give me a whole thing. Right. So let's now look at another example where we are not making a monad on set anymore, but we are making a monad on preorders. So remember that preorder was a category where the objects were preorders and the morphisms were things that respected the order. What was a preorder? It was a set together with a relation on it, and this relation had to be reflexive and transitive. So for example, the set could be the natural numbers, the relation could be the usual less than or equal to relation of natural numbers, which is reflexive or transitive. Or the set could be the booleans, where we're saying that true is smaller or equal to false. Or the set could just be some set and the relation could be equality. So there's many examples of these. Right.
It just so happens to be less than or equal to in the definition.
Yeah. Right. So it has to be, we have to think of it as less than or equal to because we want it to be reflexive. Right. So we can't have a strict inequality because that would not be reflexive. Right, and then a monotone map between these things was a function between the sets, such that if x is less than y, then in the output, the function applied to x should be less than the function applied to y. Right? So we are preserving the order relation. Okay, so what would it mean to construct a monad on this category? Well, we would need a functor on this category, so something that takes preorders to preorders and monotone maps to monotone maps, right? And then we would need to have the return. So we should have something that goes from the original preorder to whatever the functor applied to that is. We should have a join which says that if I apply this functor twice, I should be able to just go down to if I apply it once, right? And the example I have in mind here is to take a preorder, and then I want to add a new bottom element to this preorder. So I had some old order, maybe the natural numbers where 5 is less than 7 and so on. And now I'm adjoining a new element to this, and I'm declaring that this element is the smallest element of the order, right? Right, so how do I do that? Well, I can do it first for the carrier set. So I'm going to define a data type called lift of p, which is going to be this lifted thing where I add in one more thing. So I'll say that I have all of the old things, but I also have a new thing which lives in lift of p. So I inject all of the old things, I add one more thing, and because it's a data type, these are different things, right? So the data type says these are the things that exist. It's either called bottom or it's called eta of p for some p. So we often use eta as the letter for injecting old things, but kind of call it whatever you want, right? So that gives me a set. Now I would also like to make this into an order. So that means that I have to say when is one element of this lift of a, okay, so if I start with p not just being any old set, but actually being an order, then I can try and lift the carrier of that order, right? And again, I want this to be something newly generated, so I'm going to do it as a data type. I guess I could have done it with a function as well. Okay, so what do I want to say here? I want to say that the new element bottom is smaller than anything, right? Or smaller or equal to. So for all p in the carrier of p, for all q in lift of the carrier of p, I want to say that which one did I use? This one? Let's copy it. Bottom is smaller or equal to q, right? Okay, I need to give p explicitly. Okay. So this is saying that if you give me any element in this lift, then I'm declaring that there is a proof that bottom is smaller or equal to that q, right? So that gives me that bottom is smaller than everything, but I also want to keep the old order relation from the previous elements, right? So I'm going to have a eta less than or equal to which says that if I have p and p prime from the carrier of p, and if p is less than p prime in p, then eta of p is going to be smaller. Okay, let's do it the ugly way. Right, so this is the projection out of the preorder p, which gives me the relation. So I'm saying that if p is less than p prime, then eta of p should be less than eta of p prime. Right? So I'm importing the old order as well. But I'm just defining something here, right? And now it's up to me to prove that it makes sense. But there's nothing a priori that says that I have to have this. I could comment this out and it would be a perfectly fine definition, right? Just wouldn't work very well. Okay, so does that make sense? So we're adding in one new element, we're keeping all of the old elements. We're saying that the new element is the smallest, and we are importing the old order relation for the old things. Right? And here it's important that we are talking about all Q from the lifted thing and not just the old things, right? We don't want to say that the bottom is greater than all of the old things. We want to say that it's really, smaller than all of the old things. We want to say that it's smaller than all the things, right? Okay, so let's see if this makes sense. So I've defined something. I want to make it into a functor. You can ask Agda, what does this mean? Well, I need to have an action on objects. I need to have an action on morphisms. I have to show that this preserves the identity and the composition. So my action on objects needs to take a preorder, P, and produce a preorder, okay? So I can ask Agda, okay, what do I need to give in order to give a preorder? Well, I have to give a carrier, I have to give a relation, and I have to show that it is reflexive, transitive, and irrelevant, right? So the carrier is going to be my lift of carrier of P. The order is going to be exactly this thing. Okay, but now we have to show that this is reflexive. So that means that for every x, x is smaller or equal to x, right? So let's start by bringing x into scope. Because this x now lives in this data type. So it makes sense to pattern match on it, right? And we say that it's either an old injected thing or it's the new bottom element. Right? So if it's an old injected thing, then I have to show that eta p is smaller than eta p. But that's a relation between two old things, so I can use the injection from the old. Okay, I think I should make these implicit because it's going to be annoying otherwise. Okay, so now here I need to show that P is less than P and P, but I know that P is reflexive, right? So that's okay. And if my element was bottom, then I need to show that bottom is less than bottom, but that's exactly what this bot thing says, right? So I give, say, if Q is bottom itself, then I get that bottom is less than or equal to bottom, which is what I wanted. Okay, so I needed both of these constructors in order to show that this thing is reflexive. Okay, what about transitivity? So I have P and Q. So it says that x is less than y is less than z, and I have to show that x is less than z. Okay. So I now, because I declare this as a data type here, I could try and pattern match on the proofs P and Q, right? And then there's the usual question, which one should I pattern match on first? And I think I know what the right answer is, but you can guess. It's not really a bad answer. I mean, there's not really a wrong answer, right? It could be a bad answer in that we do more work if we pattern match on the wrong thing, but then we can retreat in the worst case. Okay, any guesses? Q, okay. Why Q? Right. So.
I seem to recall that you're supposed to work backwards.
Right. Yeah.
Z in it.
Yes. So that's a better argument than I had to pick one. I think it's actually better to look at P. Sorry, in the sense that if we are really lucky, X is bottom, right? And then it's really easy to show that it's smaller than anything. So if I look at P, then that might reveal that X is bottom, in which case we are done, right? Whereas if Q reveals that Y is bottom, then that doesn't help us much, right? So I think we try with P. Because in this case, because P said that the proof was that bottom was smaller than anything, then we can use the same proof here, right? But with Z instead. Okay, and here we now have that eta of something. It's a terrible name. But eta of something is less than Z. And Q says that, well, that's exactly what we want actually. Wait. Right? It's a different, sorry, really a terrible name. So this is P1, that's our goal, that eta of P1 is less than Z. What we have is that eta of P prime is less than Z. But now we can pattern match on Q, and we see that of these two options, it can't really be the first one because Q is talking about eta of something, right? And the first one is talking about bottom. So in fact, if we pattern match on Q, we see that there's only one possible thing it can be, the second one. And now our goal is that eta of something is less than eta of something. That's exactly what this thing gives us. And now we are back in P, and we can use the transitivity of P, right? To get what we want. Okay. And here finally we have to show that any two proofs of these things are equal. So let's see, what could the proofs be? Okay, so we can pattern match on the proofs, P and Q. Well, and we see that because they target different things here in the first component, it can't be the case that one is bottom and the other one is an injection of a null proof, right? So we are just left with the diagonal cases. They're either both bottom, in which case they are equal, or they are both eta of some P and some P prime. In which case they start the same, they are both eta, so we can do a Kong. Eta less than. And now we need that P equals P prime, but now we're back in the original preorder P, right? So we can use that one is propositional. Okay, so we managed to define the action on objects. We took a preorder P and we produced a new preorder where the carrier was the left of the old one, right? Now we also need an action on morphisms. So given a monotone map F, we have to produce a monotone map between the lifting of X to the lifting of Y. Right? Okay, so we can ask Agda again, what does it mean to give a monotone map? Well, you give a function and you prove that it's monotone. Right? So what should the function be? Well, it should go from left of the carrier X to left of the carrier Y. So we have some X, say. And then we can pattern match on this X. It's either an injected old thing or it's bottom, right? If it's an injected old thing, then the X lives in the carrier of X. So we can apply F to it, fun F. That gets us to Y, and then we can inject that again. Right? Whereas if it's the new bottom, then there's nothing we can do with F because F wants something in X. For all we know, X is empty, right? So we can't make up an element of X. But we have to produce something in the lifted thing so we can send this to bottom on the other side. Right? And if we want this to be monotone, then we better send the smallest element to the smallest element anyway, right? Because otherwise we wouldn't respect the order. But let's see what it means here that this is monotone. So we get X and Y. and a proof P that they are related. And we have to show that this thing we just defined on X is smaller than this thing we just defined on Y, right? Okay. But we know that X is less than Y, so we can ask why is X less than Y? Well, it's either because X was bottom, or it's because they were both injected, and we had a proof in P that they were related. Right. It's good to remove the dots because they look a bit ugly. Okay, so then if X was bottom, then because our function here is sending bottom to bottom, we still need to show that bottom is smaller than something. We know how to do that. And if they were both injected, then we have a proof P that they are smaller in X. So I think we want now, and we sent injected things to injected things, right? So it's enough to show in Y that F applied to X is smaller than F applied to Y. But again, we know that F is monotone. So we get what we want, right? So all we are doing here basically is we are pattern matching to see if we were in the old situation or if we're in the new situation. And in the old situation, we're always referring to the fact that we got something that was well behaved to start with, right? So it wouldn't work if we tried with just a set and tried to make a preorder. We really need the data coming in to produce the data going out. Okay. And then we need to show that if we apply this thing, the F map, to the identity in the category of preorders, then we get the identity in the category of preorders again. Right? And then you might think that, okay, so here we are asked to prove that two functions are equal, but it's a little bit worse than that. We're asked to prove that two preorder morphisms are equal, right? And we had this eq monotone map, I think. Which says that to show that two monotone maps are equal, it's enough to show that their underlying functions are equal. Right? That seems good for us now. And now here, we need that these two functions are equal. And again, this is not just going to work by REFL, because this function here is actually pattern matching on its argument, right? So this is a typical case where we want to use function extensionality. Right, because now we get to pattern match on X ourselves. So we could do this in a where clause. Okay, X is the scope. And I guess we need to say X here as well. That's the wrong place for it. Okay, we could also try to actually plug the lemma in here. Right. So the problem was this was yellow because there were some implicit arguments that I didn't know what they were. But if we actually use the thing, then they can figure that out from the context where it's used. Right. So then the yellow disappeared. Okay, so this is what we need to do. But now we're allowed to pattern match on X. So there's two cases. In this case, the goal is simple. And in this case, the goal is simple. So we just had to use X to get into these two simple cases. Okay. And finally, to see that we have a functor, we need to show that we are preserving composition. So I guess I'm going to bring F and G into scope. Because again, okay, I want this monotone map to be equal to that monotone map. Half of that, and then I want this function to be equal to that function. Okay, and let's just say x equals x. Because now this is what I want to show. Right. So I think, right, so I could do this again where I make a lemma and a where clause, but I think in this case, because these functions are not actually recursive, right? I think I can get away with using a pattern matching lambda here instead. Have you seen these before, the pattern matching lambdas? So it's like an ordinary lambda, but I have curly braces here. And then inside here, I'm allowed to pattern match on x. And I get these two cases, right? But I can't do any recursive calls because it's a lambda, so I don't have a name for the recursive call, right? But I can do a case distinction. And we see that in this case, it's easy. And in this case, it's also easy. Right? So it saves me from naming the lemma and giving the type of it and so on. Okay. So it's a little bit wordy, but we have defined a functor from preorders to preorders, and the important point is what it's doing on objects in some sense, right? Which is all of this, I suppose. And the important point here again is these first two lines, right? So it's saying what's our new carrier and what's our new order relation. And if you get these right, then the proofs of reflexivity and so on are going to be okay, right? Right, so we have a functor, so it makes sense to say, okay, maybe this functor is a monad. You can see, what does it mean to give a monad? Well, we have to give a functor. That's the thing we just gave, called lift. And then we have to define return and join. So we have to give a transformation. Now we can see what the type of this is. It says that for every preorder x, we need to make a monotone map from x into the lift of x. Right. So I'm going to rename this P. So now we need a monotone map from P into the lift of P. Okay, so a monotone map is a function which is monotone. So the function needs to go from the carrier of P to the lift of the carrier of P. Okay, any ideas? It's something that goes from the old thing into the new thing.
That's
so again, I guess you have a 50% chance of getting it right.
I right before it was false, but earlier I remember you saying.
Yeah, so it's not the new bottom we added, right? I mean, it's true that I could take something from the old carrier, throw it away, and just return bottom here. That would, at this point, be type correct. But it doesn't feel right, right? I think the thing that seems more promising to me is to use eta, which exactly takes an old thing and gives me something in the new thing, right? So let's see, if we just say eta here, then, okay, it goes from some p to lift of that thing. And I'm not in Agda mode anymore, okay. Okay, let me start Agda. This is all terrible. Okay, I think it's time to just restart Emacs. Okay. Right, so I think I'll make this big again. Looks like eta has the right type, right? Okay, so that's a good function, but is it monotone? Well, so monotone means that if I have two elements in the carrier, x and y, if x is less than y, then eta of x should be less than eta of y. But that's exactly what we said at eta last one. This thing. Oops. Am I right? Oh, for p. Okay, so the display here is again terrible. This is p eta expanded. We're saying that eta of something is less than eta of something. That's what we want here. Right. Okay, except here we take the x and the y explicitly. Here we took them implicitly. Okay, so the constructor we designed here exactly says that eta is monotone, right? Whereas when we designed it, we were saying, well, it makes sense that if things were related before, then they should be related also in the lifted thing, right? Okay, is this natural? X and y and f, and we need that if we compose f with return, that should be the same as doing return with f map f. Okay, that's again an equation between monotone maps. Right, and then it's easy. That's okay. Okay, what about the join? So this needs to be a natural transformation from lift of x to lift of x. So what is the transformation? Given a p, load again. Given a p, we need a monotone map from lift of p to lift of p. Okay, what is the function? So we need to go from lift of p to lift of p. Okay. We can pattern match on x. It's either an injected lift of x or its bottom, right? So if it's a lift of x, then we can just return it. And if it's bottom, then we can use the other bottom, right? So again, it's kind of a good sign that we're sending bottom to bottom if we want to be monotone. Okay, is this monotone? X, Y, P. Okay, and we want the transformation applied to x to be smaller than the transformation applied to y. We know that x is less than y. Let's look at p to see why x is less than y. Well, it's either because x was bottom, in which case we want bottom to be smaller than something. Or it's because they were both etas, in which case the transformation was just peeling off the eta, right? So we can similarly peel off this injection and just give back p, I think. Yeah, type checks. So it's monotone in both cases. So it's monotone overall. Is it natural? Well, x, y, f. We get this complicated looking equation between monotone maps. So we can say it's enough if the underlying functions are equal. What does that mean? It's still doesn't quite look obvious, right? So let's use function extensionality. Okay, then we have to do it for every x. I think we can get away with just a pattern matching thing again. Okay, so we have to do it for this. We can pattern match on the lifted x. It's either an eta of a lifted x at the bottom. In this case, it looks the same. And in this case, it also looks like we send it to the same thing. Right. So I guess the moral of this particular line is that it looked terrible to start with, but we just apply the simplification tools we have until we get something that's not so terrible anymore. Right. Okay, and then in the last 5 minutes, we should check if this satisfies the laws. So this again looks kind of terrible, right? So we are saying, well, if we compose return with join, we should get the identity. If we start at something lifted already, it's again an equation between monotone maps. Right, and then it turns out to be easy. What about this one? It's also an equation between monotone maps. Okay, this doesn't look as simple, so we'll use extensionality. And then try with a pattern matching lambda. So we have a lifted x. We want this, so we can pattern match on the lifted x. Okay, that was easy. And that was easy. Right. So you see, I'm kind of just verifying these laws, right? I'm not thinking too much about what they mean at this point. I'm just happy if I can fill all the goals, because I know that they make sense in the abstract. Right. Let's see if this last one makes sense. It's again an equation between monotone maps. So we do that. Looks like REFL might fit. No. Okay, then we use extensionality. Lifted x goes to something. Okay, we pattern match on the lifted x. Okay, now REFL definitely fits. And now REFL definitely fits. Right. So we filled all the goals, which means that we have defined a monad on preorders. And again, it's a lot of verifications, but what it's doing is basically adding in this new base element to it, right? And if you think, can you think of anything in Haskell land that does something like this? So we can't talk about preorders in this sense in Haskell, right? But we can pretend. And then this is looking quite a lot like the maybe monad, right? Because we're adding in one new thing, which is nothing, which information-wise should be below all of the things we know exist already. So this is one way to, a rather complicated way to make the maybe monad is if you start with a set, then you turn it into a trivial preorder where the equation is equality. Then you lift it like this, that adds in nothing. And then you forget that it was a preorder and turn it back into a set again, right? And you will get exactly the maybe monad. But this way we can really keep track of the more information to say that, well, we are dealing with preorders, so we are not forgetting about the order structure, right? And that's sometimes useful. But so the main thing was I wanted to show you an example of a monad which is not on set. Okay, any questions about any of this? No? Okay, then I think we stop for now and continue with monads next week.